So we'll finish up talking about loads, forces, and equilibrium by doing some thought experiments, maybe some little yoga-like experiments that will drive home, I hope, some of the principles that we've been talking about, the types of forces that structures and structural elements experience, and also some sense of how we balance these out to create equilibrium. And we'll do these using, like I said, our own bodies, right? We're familiar with structures in a kind of intuitive sense because our bodies are themselves structural elements. And we can simulate some of the forces that happen on buildings with some relatively simple exercises. So to start with, the states of stress that we've talked about, tension and compression in particular, but also bending, and then the last two, shear and torsion. These are all things that you can simulate in your own body very, very easily if you start by doing a plank. And if we start over here with bending, if you do a simple plank, right, just like get yourself into a push-up position, push yourselves up with your arms, and hold that for a little while. Pretty soon you start to experience this combined state of tension and compression. And in a simply supported beam, which when you're doing a plank, that's exactly what you are, you will experience tension in the bottom part of your body, in your abs, and compression in the top part, in your spine. Now, our bones carry compression without our really noticing it that much. So your back won't start to feel like it's doing anything. But after 30 seconds or a minute, you'll definitely notice that your abdominal muscles are working really hard. When our muscles are working, they're going into tension. They're trying basically to pull two parts of our body together. And when you're doing a plank, what you're doing is you're creating exactly this pair of tensile forces and compressive forces that make a beam work. And we'll get into the complexity of this in 347. But for the moment, just understand or do this for yourself and experience the fact that bending is really these two sets of forces acting together in the same structural element. Now, if you've ever done planks with a personal trainer, you know that they will yell at you constantly to get your butt down, right? To make sure that you've got a nice flat profile when you're doing the plank. And the reason for this is that if your butt ends up in the air when you're doing a plank, you're not really a beam, you're more of an arch. And what's happening here is that instead of building up that tension in your abdominal muscles, you're getting your body out of the way of that tensile region, and you're forming a geometry that's going to carry most of your weight to the ground through your bones in compression. Notice here that legs are straight, arms are straight, back is straight. Basically, all of this person's weight is being transmitted to the ground directly through the bones, right? The muscles aren't doing any work. For a structure, this is great. We often do bridges in particular in shapes that carry pure compression so that we don't have to worry about the complexities of bending in a large structure like a bridge. If you're trying to strengthen your abs, then this is terrible because it's actually very easy to hold that pose for quite some time without your muscles doing any real work, right? Your abs aren't going into tension when you do a pike instead of a plank, and therefore you're not building up the musculature that people typically want. Now, you can emphasize the tension in your abs by doing a yoga pose like this here, where you're actually lifting up from the ground with the front half of your body, and you'll feel for sure that your abs are tightening, right? That what you're doing is you're trying to stretch them out, essentially. When you do a plank, if you do what's called a one-armed side plank, then you'll really feel the effects of what we call shear. And shear, if you think of like kitchen shears or scissors, this is, remember, the tendency of one part of the structure to slide past the other. And this one-armed position here, very quickly you feel that there is shear stress building up in your shoulder, right? It gets painful really fast because that little joint is trying to hold all of your body up, right? Keeping all of your body from sliding past the rest of the shoulder joint. If you start to rotate back and forth, then that shoulder joint is experiencing what we call torsion, right? The tendency to twist. And we won't deal with torsion very much. We'll talk about it a little bit when we get to high-rise buildings and wind loads. Most of what we'll be dealing with, especially for the rest of this class and up through 347, will be compression and tension, what we call funicular structures that carry only one type of stress, one of these two. And then later we'll talk about what happens when we combine them into beams and the kind of more complicated but very useful state of stress known as bending. We can use our bodies, our skeleton and musculature also to think about some of these vector algebra issues that we've talked about. When we are just standing on a floor or on the ground, we have this very, very simple equation, right? Whatever our weight is, say 200 pounds, is passing directly through the centroid of our body, right? The middle, basically, of our body. And if we're standing on a piece of firm ground or on a solid floor, we can imagine that vector is getting met by an equal and opposite vector that's pushing up, right, that's keeping us from basically falling through the ground or falling through the floor. This vector is is based on the capacity of that floor's material and the shape of that floor to build up a resisting stress, right, to build up a compressive stress that's equal and opposite to our weight. So 200 pounds down, 200 pounds up, we are in equilibrium, right? We're not going anywhere. If we put someone on our shoulders, right, say someone who weighs 100 pounds, then we really have two sets of vectors that we're interested in. In the first place, we're certainly interested in what our bodies are experiencing, and we'll have a similar pair of equilibrium arrows as in the first example, but now this is actually occurring within our bodies, right, that our skeletons are actually building up this internal resistance here, the blue arrow that is equal and opposite to the weight of the person on top of us. Now, if we keep going, though, if we kind of zoom out, we can see that we also have another set of equilibrium vectors that we would be interested in. That is the pair that represents the combined weight of us and the person we're carrying, and the resistance that the floor or the ground would actually build up. So now we have the rider's vector of 100 pounds, our vector of 200 pounds. Those two combine to create a total weight of 300 pounds, and now the floor is going to have to build up a compressive stress of 300 pounds to keep us in equilibrium. Right? So notice bigger vector, equal and opposite vector in the ground. 100 plus 200 pounds there, 300 pounds in the floor there. 100 plus 200 is 300. Everything's good, right? We're in translational equilibrium. Okay, so keep that thought experiment going, right? What happens if we put 5 or 6 or 7 people on top of us? Well, we're certainly carrying that load. If we're strong enough, no problem. We'll feel it. But the other thing that will happen will be that our structure, the structure that we're building, the tower of people, will get less and less stable. Because, remember, we're not only interested in translational equilibrium, we're interested in rotational equilibrium. This is what I mean when I say that we like our buildings to not just not fall down, but also to not fall over. And eventually we would get to a height where a very, very small force acting on this person at the top would create a tremendous amount of leverage. If we think about it, the fulcrum of that lever is down here by our feet. That's a very, very long, what we call moment arm, very long wrench, if you want to think about it that way. And it's not going to take very much to knock that pile of people over. Instead, we would want to be able to kind of spread our feet out, maybe not just as far as as our own feet, but maybe we redesign the structure so that we can get a wider footprint down at the base. Now what happens is a force at the top can be met by a larger resisting moment at the base. There's a long lever arm here, but we also have a long lever arm at the base that gives us what we call a resisting moment, or if you want a resisting leverage, a resisting torque that's able to build up stress within our feet, within the floor, that can be equal and opposite not only to the vertical force, but also to what we call the overturning force, right? The clockwise force that would come about as a result of an arrow going left to right on top of that tower there. Now, intuitively, we know this, right? If we see cheerleaders building towers, they don't usually go 3 or 4 or 5 people one on top of the other without building a pyramid. And here, as you can see, the weight of each person is shared by the 2 beneath them. So spreading the load out, equalizing the load among many, many people down at the base. But also you can see that the shape is more of a triangle. Triangles are good structural shapes because they are geometrically stable. To change the shape of a triangle, you actually have to bend or break the elements in a triangle. Whereas with a square or a rectangle, you can make many different parallelograms out of 4 legs that have a fixed length. Triangle, you can only make one shape. So a triangle is stable. And as you can see here, we can trace the load path of each person down to the ground, figure out how much each of these folks on the ground are carrying. But we can also look at that as a rotationally stable shape. And we can think about what forces could happen to the top bit of the tower, what their moment arm would be around the base, and what sort of resisting moment we could build up by that base kind of spread out, right? So a way to essentially not only build up a resisting force or resisting stress to the vertical force, but also resisting moments to the overturning forces that we get in tall towers in particular. We could keep going, right? Really good cheerleading teams will build towers that are much, much lighter and that again rely on triangulation, but also rely on these principles of vector algebra that can create equilibrium. So notice here that the person standing at the top, their legs are at sort of a wide angle. Their weight, the vertical arrow here, is definitely being carried by the people on either side. But because their legs are at an angle, that weight also comes with a horizontal thrust, right? If you'll notice, the direction of the force coming from their leg is at a diagonal, right? In line with their skeleton, right? In line with their bones. Because that's at an angle, that vertical force is also going to have this horizontal component, right? It's going to come with that horizontal component. And these people here, in addition to pushing up, are going to have to push in. This is what we call a thrust. And it's a problem with any arch or any shape like this where we're taking loads at a diagonal or at an angle to the vertical. We can handle this with basically what we call flying buttresses, right? Here, this person is taking all of that vertical and horizontal thrust. They're taking the vertical force down their bodies into the person below them. Here we have a couple people who are literally just leaning in, right? Literally just propping the tower up. And you can see that they are taking just that horizontal component of this person's weight, right? These are what we call flying buttresses in structural design. And this is very much the kind of section or the kind of structural idea that you see in Gothic cathedrals, right? That the builders then, even though they didn't have the math that we had, knew intuitively that to carry the loads of, in this case, stone vaults over a fairly broad space, the weight of those stone vaults would certainly get turned into a vertical component, but that as soon as you are taking those loads at an angle, you'll also get a horizontal component. And you need something, in this case, stone flying buttresses that are leaning in and taking the horizontal component of those loads. We can design without flying buttresses so long as we have a kind of decent footprint at the base, so long as we have ways to build up that overturning moment that can knock a building over. If you look at a tower like the Eiffel Tower in Paris, it's this beautiful, kind of graceful, intuitive shape. Basically, all Eiffel is doing is making very clear how important it is when we get super tall. Eiffel Tower is about 900 feet tall. When we get that tall, it's not only gravity that we're worried about. We're also worried about the effects of wind, Some parts of the world we're concerned about the effects of seismic. And as you can see, the Eiffel Tower is basically designed with its feet spread out to brace itself against the wind, to give itself this chance to build up a resisting moment that's going to counteract the overturning moment that we get from the wind. So a way to assure that the building will stay in translational equilibrium, right? The ground is strong enough to hold it up, but also in rotational equilibrium. We're going to have a pair of reactions at either side of the tower that together are going to build up a resisting moment to the leverage that the wind at the top is going to have that's trying to tip the tower over. Now, we actually see this, right? Here's an actual kind of Bodylab experiment going on in Spain, and you can see that there is a tower here. Note that there are 3 people at each of the kind of stories, 3 people forming a triangle, right, in plan, but you can see also that they're forming a very, very broad triangle in section, right, very similar to the Eiffel Tower, where down here at the bottom you can see too that all of these people around the base are actually pushing in, right? They're not actually carrying any of the vertical load. What they're doing is they are taking up the horizontal thrust that is imparted by this tower of people gradually spreading out at the base, right? Turning that vertical load into a diagonal load that has both a vertical component that the folks in here are taking up and a horizontal component that's being helped by the people around the perimeter of the tower. We do this in vectors by looking at what we call horizontal and vertical components. So when we have force that's acting at an angle, whether that's the force of someone's leg at the top of a tower, or whether that is the force that is in an arch that's spanning over a river, we are able to look at that angle and the magnitude of the vector and break it down into horizontal and vertical components using a little bit of trigonometry. So notice here that when we have a force at an angle, that the steeper it gets, the greater the vertical component is going to be and the less the horizontal component is going to be. If we shallow that out, right, if we have a very, very broad arch, let's say, or if we've got a cheerleader who's got a really good splits going on at the top of that tower, notice what happens, that the vertical component is actually going to be much, much less than the horizontal component. We're going to have what we call a thrust that we have to take up with not just a vertical arrow acting in opposition, but with a horizontal arrow as well. In a cheerleading tower, that's going to be the kind of leaning people at the edge of the tower. In a Gothic cathedral, that's going to be a flying buttress, but it could also be something like a cable that's actually pulling on the support over here, right? Something that takes that thrust back across the span in some way. Engineers will always tell you that they prefer triangles that are steeper, that they would rather not get the big horizontal thrust that you get with these very, very shallow angles. And so, for instance, when we're doing a transfer structure, if we're bringing a column and a high-rise down and we have to get over a very big span, the engineer is going to want that transfer structure to be as deep as possible so that they can get very, very steep resultant arrows with very, very low horizontal thrusts. Same goes if we're lifting weights, right? If you've ever lifted weights with a personal trainer, they will tell you to get your feet kind of closer together. And the reason for this is that they want the load from that weight going straight down into the ground. The second your feet start to spread apart, you can see that you start to build up not only the vertical forces in your skeleton, but also horizontal ones, right? And by the time we get to like a very, very wide stance here, you can see that there's a lot of horizontal force that your hips and your feet are going to have to take up, right? In addition to the bones in your legs. So note too that the resultant is going to get greater and greater and greater. The vertical component here is the same in each case, right? The vertical component is going to be 200 pounds in each of your legs to carry that 400-pound barbell. But notice that as we get a wider and wider stance, the vertical component stays the same, but because the angle that it's being taken at gets greater and greater, we end up with a larger horizontal component, and the forces that your legs are actually feeling are going to be greater and greater and greater, right? More than 200 pounds each. It's going to be easiest to lift that barbell if your legs are straight, flat on the ground, and you're not introducing these horizontal components of those forces. Again, we can use trigonometry to show this, right? We can use sine and cosine to show that as our legs get to be wider and wider, by the time we hit, say, 50 degrees, notice that the force in our leg gets up to 260 pounds each, right? More than the weight of the barbell itself. And that is all about trying to find a set of forces, vertical, diagonal, horizontal, that are all in equilibrium, right? And the straighter we are, the more funicular we are, the more directly we're carrying those loads into the ground. So one other thing that I want to point out is this idea of bending moment, not just in terms of overturning, but also in terms of what we call a cantilever. A cantilever is any beam that has an anchorage only at one end, right? So it doesn't span from support to support, it spans from support out into space. And if you think about it, when you hold a weight out at the end of your arm, you're basically a cantilevered beam, right? Your arm is working like a cantilever. Now, think about this if you're holding, say, a dumbbell, right, out at the end of your arm. If you hold a heavier dumbbell, obviously it's much, much harder. But also think about what happens if you hold the dumbbell closer to your shoulder or farther away. If you hold the dumbbell close to your shoulder, even though the vertical force is going to be exactly the same, the moment or the torque that you're putting on your shoulder joint is going to be much less than if you're holding it out at arm's length. And if you're holding a weight all the way out at the end of your arm, you'll notice very quickly that it's much, much more difficult, right? You're experiencing a much, much greater moment or leverage on your shoulder than if you're holding it further down, right, or closer in. So this is that same principle, right, that a very, very tall structure is subject to overturning moments because of wind. Here, the longer your arm, the further out you hold that weight, even though the weight is the same, the larger the span, the greater the bending moment around your shoulder. So this gets to be really crucial, right? We're not only interested in how much load we're putting onto a building structure or a structural element. We're also concerned with where that load occurs relative to its supports. And always we'll be trying to minimize the bending moment that we're putting onto a structure. Whether that's a beam or a high-rise structure, we're looking for ways to try to either reduce the moment, reduce the dimension, reduce the weight, or to build up an adequate overturning moment, right? Enough shoulder strength, feet apart, to resist the bending or the leverage or the torque that weight will impart because of its position. This is, to me, the secret behind one of the greatest and kind of first Bodylab experiments that we know about. This is the Firth of Forth Bridge in Scotland, and it's what's called a cantilever span. So you can see there are 3 towers, and each of the towers has this great big cantilever shape sticking out of it, and then between the ends of the cantilever there are these little trusses that are what we call simply supported, right? Those are just simple beams, and you can see that they're deeper in the middle than at the ends, right? That's the trademark of a simply supported beam. Here the cantilevers are deepest in the middle, and they taper out toward the ends. And one of the reasons for that is that the elements on the top here are in tension. The elements on the bottom are in compression. And what they're essentially trying to do is they're trying to get enough height so that the tensile elements have some fall to them, right? So that they're not carrying the weight of the bridge flat, but they're actually carrying it with some vertical to it so that they can build up some resistance a little more easily. The way that the engineer explained this principle was by taking these three assistants. He put the lightest one on a little bench here, and he had these guys hold on to a set of cricket bats and then use their arms as the tensile elements to mimic the way that the bridge actually worked. Now, notice that they could do this, maybe not all day, but they could do this for quite a while, because they're not only holding up the weight with their arms. They have these compression elements here that are helping to take his weight down into the chairs that they're sitting on. Notice too that they have cantilevers going to what we call the backspan, down to anchorages on either side that balance, right, that make them into seesaws. You can think about this as the guy in the middle imparting an overturning moment, right? His weight times the distance between the center of his body and the center of the chair. And that's being resisted by an equal and opposite moment that's being imparted by the weight, which is equal to its weight times the distance between its center and the center, again, of the chair here. So this guy is imparting a moment that is going counterclockwise around the chair. The weight is imparting a moment that's going clockwise. Those two moments are going to be equal and opposite, and therefore the bridge is in equilibrium. Okay, so hopefully those illustrate maybe the stresses and the ways stresses interact within a building frame. We know some of this intuitively because we walk all around the world each day in our own structures, right? Our own structural systems composed of structural elements. Key takeaway is that these forces are important to identify, important to understand how they flow through a structure, but it's not just how much force there is, but also where those structures are. And if, in fact, we get it wrong, we can have structural failures like the one you see here. This poor plane is subjected to a very, very unequal overturning moment, and in fact, has rotated in a way that it has eventually found equilibrium, but probably not in the way that the pilots wanted. In the next lectures, we'll start to apply some of these, and we'll start to look at how forces flow through structures, how we can design them to adequately direct them, adequately resist the loads that we're putting on them, and how these end up with very, very often repeated and very familiar structural shapes.